Hello, welcome to part 3. Here we will discuss utilizing selection tools and how to identify true genetic differences so we can make meaningful selection decisions. Identifying genetic differences is a key step to making selection decisions where progress can be made. We have to remember that phenotype, what we observe, what we see in an individual animal, is the result of their genotype, the genetics of the individual, plus the environment. And remember, environment varies from farm to farm, region to region. And so environment does not stay constant. So what we observe in terms of weaning weights, or what we observe in terms of the way an animal looks or appears, is influenced by both genetics and that environment. That environment cannot be passed from farm to farm, but the genetics can. Genetics can be passed from farm to farm. Genetics can also be passed from one generation to the next. So we need to be able to isolate and understand what's genetic versus what is environment so that we can accurately identify the genetic component, select for that genetic component so that we can make progress in our operations regardless and independent of environment. So what selection tools do we have available for our production systems? We have records, and records are the first place to start. They're the fundamental foundation of genetic evaluation. We have to have records before we can do anything. And records allow us to establish benchmarks for moving forward. Records, though, are a phenotype. They are a form of phenotypic selection. So if we select for records alone, there is an environmental component to that, and the accuracy of our selection decisions won't be as strong. So if we can identify or separate out the genetic component from those records, that would really be ideal. And that is what estimated breeding values allow us to do. Estimated breeding values provide us with a form of quantitative selection that measures individual genetic merit. Estimated breeding values represent that genetic component independent of environment. These estimated breeding values combine individual performance, pedigree information, as well as progeny data to give us a much more accurate tool, much more accurate resource to make selection decisions and move our flocks towards our goals. These estimated breeding values are the best tool we have in our toolbox. And so while records are very important and they should be kept regardless, it's really the estimated breeding values that when it comes to selecting and identifying those breeding stock, those rams or those bucks to utilize in our breeding programs should really be based on these estimated breeding values as they are our most accurate form or our most accurate selection tool. So what are some important records? There's many records that are important, and you can, depending on your production system and what your market is, there's a variety of different things that you could keep records on, but these are just a few examples. Birth dates, birth types, so whether they were single, twin, or triplet, birth weights, sire and dam is a parentage, and forming those pedigrees is really the foundation for making and establishing a good genetic breeding program. Rearing type and how many lambs or kids that female was actually able to raise to weaning, the date that weaning took place, weaning weights. Peak lay counts are a very valuable record when it comes to parasite resistance and understanding the level of parasite resistance within a flock or herd. FAMACHA scores are also very valuable and can be combined with some of those deworming records to understand the susceptibility of your animals and their needs for deworming. Market weights, carcass traits, wool traits are metrics that can provide us with some in-product value and a better understanding of what the value of the output that those animals are generating. Hair shedding is one that if you're raising hair sheep and don't want to shear and need animals that shed is a trait that could be recorded. And for any of you that may be dairy producers, milk production is key to understanding and increasing the production of those dairy animals. Remember, if you don't measure it, you can't select for it. And it's important to write down all of these records because our brains, our minds, we're all human and they will fail us. And so writing it down and having those permanent records is really ideal. So these estimated breeding values are a measure of individual genetic merits. They are that numerical representation of genotype. So when we talk about genotypes and that genetic component, these estimated breeding values are simply a number that represent that genotype. These estimated breeding values allow for quick and easy comparison between individuals for those economically relevant traits. They represent the expected performance of an individual compared to another individual in the same breed. These estimated breeding values are only relevant or can only be compared within breed. We can't, in sheep and small ruminants, we cannot compare them across breed. So only within breed, they can be utilized to compare one individual to another and the expected level of performance relative to that individual's genetics compared to one another. Remember, breed average is not always zero, and we'll provide more information about this in future parts. So if we go back to that equation that I provided at the beginning, phenotype equals, is a combination of genetics and environment. We can take these breeding values and insert that breeding value for that genetic component and think about that phenotype being a result of the breeding value of the individual, the genetic merit of the individual, plus the environments that they're exposed to. So how are EBVs generated? How are these estimated breeding values predicted? The first step to generating them is to measure those phenotypic traits of the individuals, to keep records. That is the foundation of genetic evaluation and establishing these breeding values. So step one, we have to measure those traits that are relevant to our production system. That could be body weights, that could be carcass measurements, reproductive measurements like number of lambs born, number of lambs weaned, wool traits if wool production is of value to you, fecal egg counts if you're interested in improving the parasite resistance of those individuals. Step two, we need to account for those environmental differences. We need to separate out what is genetic versus what is environment. We need to account for those sources of variation that we understand. We know that birth type will influence the pre-weaning performance of an individual. We know that age influences her milk production and the weight of lambs at weaning. Feeding and housing systems can influence pre-weaning and post-weaning performance as well. We can take all those things into account. Unfortunately, we don't have to do this math on our own. There's computer programs and systems in place to do this for us, but we separate out what is genetic versus what is environment. So we take the environmental component out of the picture. So all we're left with is the individual animal, that phenotype being associated with genotype. And if we can identify the differences in that phenotype that are a result or a consequence of the genetics of that individual, then we can select for those genetics and make meaningful change. So like I said, there's computer systems to do this. The goal or the requirement as a producer is to simply collect these records, submit them, run them through the National Sheep Improvement Program and the Land Plan system. This math is done for you, the statistical analysis is done for us, and we simply get those breeding values back. So we've collected the records, we've accounted for those environmental differences. And by doing so, we take into account the heritability. And the heritability is the portion of what we observe, that phenotype, that can be explained by genetics. It's simply the genetic component of a given trait. Typically, this heritability is expressed as H squared. So if you see H squared, think heritability, and it can range from 0 to 1. A trait that has a heritability of 0 is a trait that has no genetic component. A trait that has a heritability of 1 is a trait that is 100% heritable, or a trait that is 100% controlled by the genetics of the individual. The higher the value, the greater the heritability, the greater that genetic component. On average, though, for most of our traits, only about 20% of what we observe is a result of genetics. The rest is environment. So here's the heritability for a variety of different traits. Our weight traits, like birth weight, weaning weight, post-weaning weight, are what we call moderately heritable. They range from about 0.15 to about 0.25. So 15 to 25% of what we observe in those traits is a result of genetics. The rest is all environment. Our reproductive traits like prolificacy or milk production are lowly heritable, about 10%. So 90% of what we observe in the prolificacy, whether an animal is born a single, twin, or triplet, 90% of that is controlled by environment. Only about 10% is genetic. The carcass traits like ribeye area, fat thickness, those are highly heritable traits, 30 to 35% on heritability. Parasite resistance falls in that moderate category, about 20%. And our fleece traits, our wool traits, are actually our most highly heritable traits, upwards of 40 to 50% on heritability. So by and large, the vast majority of what we observe in an individual's performance is a result of environment. Nonetheless, that in genetic components is very important, because remember, the genetic component is what's passed from generation to generation. That can be transferred from farm to farm through the purchase of rams or ewes, purchase of breeding stock, where that environmental component cannot be moved from one location to another necessarily. So while environment is going to vary, that those genetics are able to be passed along. So if we can identify that genetic component, that is ideal. So after collecting the records, accounting for those environmental differences and separating out what's genetic versus what is environment, we then analyze those pedigrees and compare an individual and animal to all of its relatives, all of its known relatives in that pedigree. So that'd be mom and dad, aunt and uncle, grandparents, and any progeny that may have been produced as well. So we get the full picture, this full scope in understanding what is the true genetic merit of that individual based on not only its own performance, but the performance of its relatives. We then isolate that genetic difference between individuals from that environmental differences, account for those environmental differences, compare to all the relatives, as I mentioned, and we assign that numeric value to genetic merit and determine what that estimated breeding value really is. These estimated breeding values are so powerful because the environmental differences, that environmental component, is eliminated. These EBVs are independent of environment and can be compared and analyzed across flocks. So I can compare the EBVs on a Katahdin ram here in North Carolina to one in Kentucky or one in Oregon. And those, they're still meaningful and have value and are representative of their true genetic merit. As long as we're within the same breed, they can be compared across flocks. Because of all the reasons I mentioned and the data that go into generating these EBVs, these estimated breeding values are more powerful than our raw data, such as weaning weights. They're more powerful than adjusted weights, adjusted data like 60-day adjusted weaning weights, and they're more powerful than ram or buck tests. And so really these are our ideal tool for selection. And as a reminder, goats are eligible for the National Sheep Improvement Program, and we can generate estimated breeding values for goats. So some important EBVs within the kind of the maternal category, we have number of lambs born, number of lambs weaned, as well as maternal weaning weight, which that's our indicator trait for milk production. For growth, we have weaning weights and post-weaning weights. We have carcass measurements like eye muscle depth as our indicator of muscle development, muscularity. We have fat depth as an indicator of trimness. For fitness traits, we have an EBV for fecal egg count, which allows us to select for parasite resistance. We also have indexes that combine multiple traits into one number and simplify our selection. So we have what's called the Carcass Plus Index, the maternal index, as well as a hair index that allow us to select for multiple traits at the same time and do so in an accurate way. So it can simplify our selection. So instead of trying to decide between multiple traits where to place emphasis, these indexes help do that for us. So these traits within an index are economically weighted to simplify that selection and apply appropriate selection pressure to each one of those traits based on their economic relevance. Remember, the more traits you select for at a given time, the less progress you'll make in any one trait. So these indexes have identified the key traits in different types of production systems, whether that's a maternal production system or a terminal production system, identified those key traits, weighted them based on their economic relevance, and now we can select for 3 or 4 traits at the same time with appropriate selection pressure. So the hair index would be our maternal index for hair sheep, for Katahdins primarily. This index includes weaning weight, the weaning weight EBV, the maternal weaning weight or milk EBV, the number of lambs born EBV, as well as the number of lambs weaned EBV. The Carcass Plus Index is our index for terminal sires. indicating the value or potential value in carcass or in product from those terminal matings. This carcass plus index includes the EBVs for weaning weight, post-weaning weight, eye muscle depth, and fat. So we have those growth traits as well as the carcass traits. As an example, this will demonstrate the value of EBVs in different flocks and some of the differences that you may see. So in this scenario, we'll walk through an example here. We have two rams. We have ram A and ram B, and their EBV for weaning weight is provided in this table. Ram A is at 9.6, ram B is at 5.2. The difference here between those EBVs is 4.4 pounds. So if we look at the EPD, EPD simply stands for expected progeny difference. An EPD is simply half an EBV. An individual transmits half of its genetic material to its offspring. So the difference between an estimated breeding value and an expected progeny difference is just 1/2. So we take the EBV, we divide it by 2, and we get the EPD. So the EPD for ram A is 4.8. The EPD for ram B is 2.6. So the difference in EPDs is 2.2, half the difference between the EBVs. So we're going to take these two rams and we're going to breed them, or we're going to utilize them in two different flocks. So we have flock A and flock B. So we use both of these rams breed ewes in each one of these flocks. In flock A, the progeny of ram A average 48 pounds at weaning. The progeny of ram B average 45.8 pounds at weaning. The difference being 2.2 pounds. In flock B, the progeny of ram A weigh 52.3 pounds, and the progeny of ram B weigh 50.1 pounds. While these progeny are heavier overall, the difference in weaning weight between progeny of ram A and ram B is still 2.2. So while the actual weaning weights of lambs may vary in different environments, the differences between the progeny of these two rams remain similar and the same, or what we would expect based on the EPD, that expected progeny difference. So you can see that while there may be environmental differences, in some flocks and some farms in some regions of the country, lambs might weigh a little bit more, a little bit less. Those relative differences are going to be very similar to what is predicted based on those genetic values of the rams. So it's not about predicting what that ram is going to produce in progeny for a specific weight. These EPDs, these EBVs will not predict an actual weight. Rather, they tell us, or they help us predict or estimate what the difference will be, the relative difference. It's all about differences. It's not predicting a specific weight. So we want to evaluate the difference in EBV between two individuals and use that to make those selection decisions. Don't use that EBV to try to predict the exact level of performance, because the level of performance is going to vary based on environments. Those differences should remain relatively constant. We also have estimated breeding value for fecal egg count. And this fecal egg count estimated breeding value was developed at Virginia Tech in the early 2000s by Dr. Dave Notter's lab. The heritability of fecal egg count is between 20 and 25%. So as I said, it's moderately heritable, and it's reported as a percent change. So a percent increase or a percent decrease in fecal egg count. So that means negative values are good. Negative values mean that that individual has the genetic potential to reduce or lower fecal egg count. So by lowering fecal egg count, we lower parasite burden, and we would expect that individual to be more parasite resistant. So low fecal egg count is good. Negative fecal egg count EBVs are good. So the fecal egg count estimated breeding value, as an example, we have two rams here. The ram on the top, its fecal egg count estimated breeding value is negative 60%. The ram on the bottom, his fecal egg count estimated breeding value is negative 10%. Because an individual only passes half of their genetic material to the offspring, the progeny of ram A would be negative 30%. The progeny of ram on the bottom would be negative 5%. Remember that EPD is equivalent to 1/2 of the EBV. So if we were to mate these two rams to the same set of ewes, we would expect the fecal egg count difference between the progeny of these two rams to be about 25%. So by utilizing that ram on the top, I can lower fecal egg count by about 25% in the offspring versus using the ram on the bottom. What about a weaning weight example? In this example, the ram on the top has a weaning weight EBV of 5 pounds. The ram on the bottom has a weaning weight EBV of 1 pound. Each pass half of that genetic material onto their offspring. So if I were to use the ram on the top versus the ram on the bottom, those lambs would be expected to be about 2 pounds heavier, because that the difference in the EPDs, the difference in the expected progeny differences is 2 pounds. So if I were to use the ram on the top versus the ram on the bottom, these lambs on average will be about 2 pounds heavier. And if that market price is about $2.50 a pound, then this difference is worth about $5. So by utilizing the ram on the top versus the ram on the bottom, for every lamb that he produces, that lamb is worth an additional $5 compared to had I used the ram on the bottom. So our selection decisions can have direct impacts on the value of our progeny, the value of our lamb crop that we are generating. Another example of this can be shown utilizing maternal EBVs. In this example, ram A has a number of lambs weaned EPD of 0%. He has a lamb weaning weight EPD of 0 pounds. Compare that ram to ram B. Ram B has a number of lambs weaned EPD of 5% and a lamb weaning weight EPD of 1. So I need to choose, do I use ram A or do I use ram B? And what's the potential economic difference or side effects of using one ram versus another? So for our scenario, we're going to use one of these two rams for 2 years, mate them to 50 ewes each year. So 100 total ewes will be bred by one ram or the other, depending on what ram we decide to use. Our average number of lambs weaned per ewe is 1.5 lambs, 150% lamb crop. So we're going to wean a total of 150 lambs per sire. So over their useful life, over those 2 years, we're going to get 150 lambs out of one ram or the other. From that, we're going to retain 25% as replacement ewe lambs. So we're going to keep roughly 38 replacement ewe lambs from one of these matings. Those replacement ewe lambs are going to average 5 lambing events in their lifetime. So in total, 5 times 38, 190 total lambings by replacement ewes. Our average weaning weight is 50 pounds. And we're going to assume that the flock currently has an average weaning weight EBV of 0 and an average number of lambs weaned EBV of 0%. That's our scenario, and those are our assumptions. So daughters of ram A. Daughters of ram A has number of lambs weaned EBV of 0%. Lamb weaning weight EPD of 0 pounds. We're going to have 190 total lambings from daughters of ram A. They're going to produce 150% lamb crop. So that's 285 total lambs weaned, 190 times 1.5. We have 285 total lambs weaned. Each one's going to weigh 50 pounds. So that's 14,250 pounds of lamb. What about daughters of ram B? So what if we used ram B instead of ram A? We used ram B, our number of lambs weaned EBV is 5%. Our lamb weaning weight EPD is 0.5. They pass half of that in the lambs and the progeny. It's going to be half of what those daughters are going to have themselves. So 0.5 on the weaning weight EPD there on the daughters of ram B. We still have 190 lambings. So we still have the same number of lambing events. But now, because they have that improved prolificacy, they have that increase in number of lambs weaned by 5%. We're now weaning 157.5% lamb crop. So we increase our lamb crop percentage by 5%. So now we're weaning 299 lambs. Those lambs, because there's an additional genetic merit for growth, those lambs now weigh 50.5 pounds. So they're a ½ pound heavier. So now we take 299 lambs that now weigh 50.5 pounds each, and we get 15,099.5 pounds a lamb. So if I were to use Ram B instead of Ram A, I have more lambs produced. Each lamb that I produce is going to weigh more. I have more pounds of total marketable lamb. So I have about 800, just shy of 850 pounds of additional lamb weans. If that lamb is valued at $2.50 a pound, that's $2,123.75 worth of lamb that I have by using Ram B that I would not have had by using Ram A. If we want to break this down further, about $1,700 of that is a result of the 14 additional lambs being sold, that increase in prolificacy, and $350 of that is from that additional lamb weight. By making this selection decision, by utilizing the ram that has superior genetics for prolificacy and growth, I have a direct impact on my bottom line through a greater weight, greater number of pounds of marketable lamb through the daughters that ram is going to produce. So you can apply this math to your given production system, your scenario, the rams you potentially have available, and evaluate what's the potential economic differences that we may observe by choosing one ram versus another. So utilizing these genetic tools, it's going to vary some based on the type of producer that you are. If you're raising purebred breeding stock that you're going to sell to commercial producers or other breeders, then I encourage you to enroll your whole flock in NSIP. Enroll the whole flock in National Sheep Improvement Program. This includes both your rams as well as your ewes. Utilize these estimated breeding values in your sire and replacement ewe lamb selection. And then market those rams, market ewes based on EBVs. Use those EBVs to help determine what the value of those individuals is. What if you're a commercial producer? If you're a commercial producer, you don't necessarily need to enroll your whole flock in an NSIP. The key here is to purchase rams based on EBVs for those economically relevant traits. Remember, after just 4 generations, over 90% of the genetics in your flock will be the result of sire decisions. As a commercial producer, you don't need to have EBVs necessarily for your ewes. If you use rams with strong EBVs for the traits you're interested in, after just 4 generations, most of your genetics in your flock will be representative of those EBVs anyway. So purchase rams, make sire decisions based on those EBVs, and in a relatively short period of time, you will observe the improvement in performance, the improvement in those economically relevant traits through just those sire decisions. So that provides some background on the selection tools that are available to us, how we can utilize those tools, and the potential economic outcomes of utilizing those tools in our selection programs.